We need to be careful when we're doing these prediction lines because computers make it really easy to make these predictions, even with a really large data set. But the computer is happy to do this calculation even if there's a curved relationship. So we need to be aware that the computer has no ability to reason whether or not this scatter plot is an appropriate relationship to try to draw a line into it. Also, the computer has no idea which variable should be the explanatory variable and which variable should be the response variable. So it's up to us as the thinkers to tell the computer what to do only when it's appropriate. So for the fossil bone explanation, it was very appropriate for us to do a regression line because the data fit that line very, very well. But the GDP data would not have been as good to try to fit a line. Even though the computer would have done it, it would not have been a very accurate model. Even the percentage voting was not that great of a model to try to do predictions. Now, I will make a note here that often we will use several explanatory variables to predict a response. It's rare for us to find exactly one variable to predict the response in another. However, in this class, we're not going to be doing these multiple variable regression lines. But if you study more statistics, that's one of the things that happens pretty quickly in the second statistics course that you would take, is looking at how to use multiple variables in order to make predictions. But if you think of applications of this, the admission process for four-year colleges typically look at lots of different indicators as to how successful they think you will be at their school. So maybe they'll look at your SAT scores, maybe your high school grades in English, math, science. So they're often going to be looking at multiple variables to try to predict first-year college grades. So it's really kind of a messy process to do this, but all of these methods of predicting a response share the same basic properties as what we're doing just with the single least squares regression line. So by understanding how the single regression line works, it will all apply if you ever need to do one of these multiple variable regression lines. So taking a look at these two examples, we're trying to fit a model to our data. The straight line model on the left is excellent. The straight line model on the right is not nearly as good. So your prediction is going to work the best when the model fits the data closely. So you would feel comfortable with the prediction in the left model far more than you would feel comfortable with the prediction on the right model. If your variables don't have strong patterns, the predictions aren't going to be very accurate. Another thing that's really important when we're dealing with this prediction is that if you try to make prediction outside of the range of the available data, it's going to be really risky. So to help you put this in perspective, think about a child's growth from age 3 to 8. Children are often growing quite rapidly during that period of time. So you might find a really strong relationship between their height at age, one age and then their height at a later age. But if you were to try to use those same prediction models of how a child was growing from age 3 to 8, and you tried to do that at 25, you're going to end up with somebody who's 8 feet tall, which really doesn't happen very frequently. Because what happens is at about maybe between 14 and 17 for most people, they stop growing. So it's not reasonable for us to think that the pattern that's happening as a child is going to continue into an adult. So this is an idea of extrapolation. So extrapolation is where you assume that the pattern that's happening in the data you have is going to continue on later. And there's a lot of things that the pattern just won't continue, such as growth. So that's why a lot of our predictors end up being wrong, even for things like meteorology, trying to predict the weather, because if you're going well beyond the available data, there's just so much that can change, and it might not follow the pattern that we've established. So be aware anytime that you're trying to make a prediction outside of the range of available data, and that's called extrapolation. So we can also see this in an example of looking at the national deficit. So every year, the Congressional Budget Office is required to submit annual reports that predict the federal budget and its deficit or surplus for the next 5 years. Now, you can imagine that trying to predict the future for 5 years is going to miss a lot of things that could be changing. There have been many events that have happened that nobody could have predicted. In 2001, nobody could have predicted that 9/11 was going to happen and disrupt the economy. Nobody predicted in 2008 that we would have hit a recession and disrupted the economy. And certainly nobody could have predicted that in 2020, COVID-19 would have disrupted our economy. So even though they're required to make a prediction for the next 5 years, that's based on policies remaining unchanged. And that is so unreasonable for us to expect. And so the forecast that was made in January 2008 underestimated the deficit by nearly $1,000 billion. That's a tremendous amount of money. That's $1 trillion. And nobody could have predicted what was going to happen in the economy.